Well, here's another example where we're finding a whole lot of different things, the tangent vector, normal vector, tangential and normal components of acceleration at t equals 0 for the space curve. Now we're going to do a space curve. And so...
Make it so, number one.
Yes, we're about to make it so. So here is the space curve. Vector value function r of t equals e to the t cosine ti plus e to the t sine tj plus e to the tk. There we got a little k factor coming into this one. So the velocity vector, of course, is just the derivative of the vector value function itself. So first d second plus second d first. Well, there's second d first. I have minus first d second. I hope you see that all right. And that's times I. And then first d second, there it is, plus second d first derivative of e to t is just e to the t, and then derivative of e to the t for the k part. And so at the time when t equals 0, we have e to the 0, which is 1, cosine of 0 is 1, sine of 0 is 0, so we got 1 times I, plus, same reasoning, 1 times j, plus 1 times k. So the length of the velocity vector at t equals 0 is 1 divided by the square root of 3. So our acceleration vector, we would take the derivative of this vector, as bad as that may be. Of course, I got the derivative of the k part down already. That's done. The derivative of the I part, we need first d second plus second d first minus first d second plus second d first. So here it is. First, actually I have it, I have second d first here, right? Minus first d second is actually plus first d second, okay? And then I need to find the derivative of this part with a negative sign in front is e to the t cosine t. This is all in quantity plus e to the t sine t, but remember that's all minus, it's subtracted, so therefore these SIGN signs are correct, times I. And similar fashion, you could probably follow this derivative as the derivative of this part right here, right? And then finally simplifying, this and this cancel out. So we got negative 2 e to the t sine t I plus, now what for this part we have canceling out the e to the t sine t, this negative e to the t sine t, right? They cancel out. And so we got 2 e to the t cosine tj plus e to the t times k. So at 0, that would be negative 2 times e to the 0 is 1 times sine of 0, which is 0, so it's 0i, 2 times 0 times 2 times e to the 0, which is 1, times cosine of 0, which is 1, so it's 2 times 1, so 2j, and e to the 0 is 1k, so we got 2i plus k. And our unit tangent vector is the velocity vector divided by the length of the velocity vector. So the velocity vector, we have that up here, divided by its length. So that could be tricky. But the length we've already determined was, if you take the time to bull through this, the length of this vector, we've got the square root of this squared. Well, what would that give us? Oh, big royal mess. Why don't we just call it square root of 3 times e to the t. Now where's that all come from? We need the length of this vector right here. Oh dear. So that would give us square root of e to the t squared cosine squared t minus e to the t squared sine squared t no, plus e to the t squared, sine squared t, and then minus 2e to the 2t, well, e to the t squared, it's e to the 2t, times cosine t times sine of t, that's got a negative sign on it, plus e to the t squared cosine squared t, or e to the 2t cosine squared t, plus 2 e to the 2t cosine squared cosine t sine t, and that's going to cancel out with the middle term from this part, plus e to the 2t sine squared of t, and what's going to happen there, the sine squareds are going to go away, and then plus e to the t squared, that's e to the 2t, so square root of e to the 2t, and what winds up being e to the t, and somehow we wind up with a square root of 3 in there. Let me see why that would be. Because we had 1 from this squared plus this squared, and we had a 1 from this squared, right, when we factor out the e to the 2t. So we have 1 plus 1 from squaring this and adding this squared, so we honestly do wind up with square root of 3 times e to the t. It's a little long, but I think you could probably see that. So, what does this wind up being? Well, what it winds up being is the e to the t and the e to the t in the vector v part cancel out. So we have the constant 1 over the square root of 3, because that didn't cancel out, times the e to the t's canceled out, so our vector is cosine t minus sine t I. Again, the e to the t's are canceled, so cosine t plus sine t j, and the e to the t's canceled, plus 1 times k. Wowzers. Okay. Unit tangent vector evaluated as 0. Well, since cosine of 0 is 1 and sine of 0 is 0, we got 1i, ditto 1j, and 1k. So 1 over the square root of 3 times I plus j plus k. Notice it's a unit vector. Hope you notice that. So the normal vector would be the derivative of that unit tangent vector divided by its length. And so, wow, that means the derivative of this, which isn't too awful bad, because the derivative of sine is cosine, so there's where the negative cosine comes from. Derivative of cosine is negative sine, so it's negative cosine t minus sine t I. Derivative of this part, we've got derivative of cosine is negative sine t. Derivative of sine of t is positive cosine of t times j, and then of course the derivative of k is just 0, so we got that divided by the length of that vector. And so if you take the time to work that out, you do get 1 over the square root of 2 times cosine t minus sine t I plus negative sine t plus cosine t j. When we evaluate that at 0, cosine of 0 is 1, sine of 0 is 0, so we get negative I. For this one, sine of 0 is 0, cosine 0 is 1, so we get plus 1j. And at t equals 0, we've got the tangential component is the acceleration at 0 times unit tangent vector at 0, which is square root 3. The normal component, dot product of acceleration vector at 0 dotted with normal vector at 0, and that comes out square root 2.